So we were talking about these things where we had the different phase changes, where if we had a phase change, it essentially flipped all of our crests into troughs. And so if we wanted constructive interference, we would have to now be off by half of a wavelength, because the phase change immediately puts us off by half a wavelength, so that if our path length difference was a full wavelength, they'd be off by half a wavelength. So the condition for constructive interference with a single phase change was essentially the condition that we used to have for destructive interference. Now, if you're working this out from scratch, while it's inside this substance, you have to pay attention to that the wavelength will change. Whenever a wave changes mediums, the speed changes and the wavelength change, but the frequency stays the same. That's an important concept. The frequency stays the same. And so the wavelength will change, which means you have to pay attention to how many of the new wavelengths there is in a difference there as it goes through that new medium, which is done, where is it? It's done here. You have to worry about what that wavelength is inside the medium, because that's where it's changing. That's where it's going inside of there. And so that gives us this result right here. And this is for destructive interference, even though it looks like constructive interference, because we don't have that 1/2 in there. And that's because we have that single phase change. If we have no phase changes or 2 phase changes, then this would be what we would do for constructive interference. All right, so just be careful about that. This here is the condition for constructive interference. Notice here, we've got that 1/2, putting it off by half, because here, to have constructive interference, the phase change throws us off by half a wavelength. So then our path length has to be off by half a wavelength too, so that they cancel each other out. 1/2 and 1/2 is a whole, right? So does that make sense to y'all? I see one person nodding. I tried the other day, it didn't go very well, because they're moving waves. So think about it this way. Let's say we had 2 waves that were in sync, right? Right, we had 2 waves that are just right nice and in phase like this. What would happen if one of them suddenly was flipped upside down, had a phase change of half a wavelength, all the crests flipped over to troughs? They'd suddenly be canceling out, correct? So what would I have to do with the red wave up there in order to get them back in line? Shift it by half a wavelength, right? I would have to take that red one and shift it forward by half of the wavelength, so that it then, or shift it back, either forward or back. Now they're back to being lined up. That's essentially what's happening. We have that phase shift that makes them out of alignment, and so then you need that extra half a wavelength in the path length difference to get them back in alignment. Yes, it's interference with its own reflection. Yep. Except, you know, again, this is occurring when you have it such that there is one phase shift. Like this is air out here, this is air out here, and this is air in here, such that, what was on this page? Wait, where was it? Right here. We have air out here and air in here. So right here, we're going from a low index to a high index, which means we're going from high speed to low speed, which means that low speed one can't react. It's like that fixed boundary, and we get a phase change. Upon going on the inside of the bubble, it's air in there again. It's going from high index, right? High index to low index, which means it's going from low speed to high speed, which means that high speed one can react, and it's like that free boundary, and we don't get a phase change. We don't get an inversion of the wave. And so we get one phase change and not another. Now, you could imagine if this was a slightly different situation where, say, like this was n equals 1.33, and then it came into here and this was 1.5 or something like that, we'd have 2 phase changes. it would phase change and phase change. So they'd both be phase changed by half a wavelength, which means our condition for constructive interference would be the normal one, where it would be this one. It would be this one without the 1/2 shift, right? And then destructive would be back to being this one where we have the 1/2 shift. Okay, so you just have to pay attention to how many phase changes you have, essentially. The book does it a little different. They like to start adding up. This one's off by half, and this one's off. It's the same thing. They're just talking about it in a slightly different way. I'm trying to simplify it down. They're like trying to do it just purely mathematically. I'm trying to just kind of make you see how many phase changes were there. If it's an odd number of phase changes, then these are the equations you use. If it's an even number or 0 phase changes, then you flip-flop them. This becomes destructive and the other one becomes constructive. Okay? Good? All right. So moving on here. Here you can see, again, they're talking about it again, the same sort of thing about how many phase changes occur. The picture on the left, there's 1 phase change. The picture on the right, there's 2 phase changes. How about that? I picked 1.5. I wonder if I did that subconsciously or something. For the 1.5. Huh? I do have example problems, and we'll do them in a bit. Okay? I'd like to get through this because I'd rather do example problems on Zoom than try to teach all of this via Zoom on Friday. So I want to get through the chapter, and then we'll go back and start doing the example one. So there's not a lot left. So here, same sort of thing with CDs. The original CDs, they actually stamped them. They had grooves on them. And so you could get different kinds of interference based on the pattern on them. And in fact, if you ever looked at a CD, the bottom of a CD or a DVD, they're all what as you move them around? Huh? Yes, but what kind of a reflective when you look at them? They're all rainbowy, right? And because of that, you're getting that same sort of interferences that are occurring on the different depths. Okay. The next thing is diffraction. This is the bending of light around a corner. Whenever it goes through, it bends out. The smaller the slit, the more diffraction you're going to get, comparative to the whole thing. If you have a very large slit compared to the wavelength, then you're not going to get as much diffraction. Now, typically sound waves are much shorter wavelengths than, or much longer wavelengths than light waves. So it's a lot easier to hear around a corner than to see around a corner, because the sound waves will diffract more around a corner than a light wave will. But anyway, it does that. It spreads all out. Okay. And that's what I was just talking about. Easier to hear around a corner than see around a corner. So now we can get the single slit interference here. You'll notice the central bright fringe is twice as, it has twice the angular, that angular length than the other ones do, because it's essentially 2 bright fringes together side by side. But essentially, because the light diffracts, you can get light from different spots inside of there interfering with itself. So it's similar to that double slit. In fact, the double slit is like 2 of these single slits on top of each other interfering. And so if you ever do get to look at a real double slit, what happens is you actually end up with the double slit interferences like superimposed inside the single slit. So the single slit, you have like the super bright and then little like this. And when you get the double slit going, what happens is you end up getting all the interferences like this, and it's like they're kind of inside that double slit like that. And so you see a bunch of more lines, but that's because they're like inside that envelope of the single slits, because the single slits are practically on top of each other. And so you end up with something like that, despite my horrible drawing there. Okay, and so then you can just look at this this angular distance here, and you see we have a slit width of W, and then we can come in here very similar to the double slit and get the angles to the dark fringes. W being the slit width, lambda being the wavelength, and then theta being your angle, so the sine of theta. Okay, and you're essentially taking it as though you have light coming from all over inside of there. Same thing here, but just talking about it coming from all the different places there as it spreads out. And then you've got your second dark fringe. Notice it's W sine theta equals lambda, and then 2 lambda, and the next one would be 3 lambda, and ultimately gives you this right here, where M is the dark fringe order number. Notice this one does not start at 0, but it tells you the angle out. And this is also why your central bright fringe is wider than the others. Angularly, it's got a wider angle to it, because you have to go like, so if you find that your angle to the first dark fringe, if we come back here, you find the angle to your first dark fringe is this angle, say it's that angle theta, and then to your first dark fringe down, it's also a theta. It means the total angle is 2 theta between those two. But if I go up to this one, then that's just not the case. You know what I mean? So I have just this smaller angle between the other ones. It keeps stepping up those angles. That would be another theta up like that. So that's why that central one is twice as bright. Like I was saying, it was like it was 2 bright fringes side by side. Okay. All right, let's keep going here. So that's a good equation right there for your dark fringes. And then your bright fringes are going to be in between those. And I've never really gotten that thing at the bottom to work. I've seen it in many textbooks where they show the guy pinching their fingers together and seeing the bright. I've never been able to see it. You know, I guess maybe you can a little bit, but yeah. So holding your finger and thumb very, very close together, right? It helps not to be too farsighted, and try and look through there and see if you can, I don't know. I'm not exactly sure. Like all the pictures I see, it shows like all these lines coming out of it, and like you see, but I don't know. I don't really see it, but whatever. I don't know if there's a nice picture of it in your book, but yeah. I'm not sure what you're supposed to see there. Like literally the pictures I see, it's like a thumb and a finger, and there's all these bright and dark lines shooting out of it. And I'm thinking, I never see anything quite as impressive as like the little drawing they have of it. So who knows? And we can look at this in the lab next week. I'll show you, well, we can look at some diffraction stuff. So anyway, diffraction through a small circular aperture results in a circular pattern of fringes. This limits our ability to distinguish one object from another when they are very close. Have you ever experienced this driving at night and you look out and you see a light coming and you can't tell if it's a single light, like is that a motorcycle or is that another car? But as it gets closer, it either stays one light or starts to split into 2. That's you being able to resolve it with your eye until the 2 light sources apart. But you see them and they look like one, and then they kind of start to look like, you know, they're widening out and they look like an 8 or something, and then they start to separate. And when you can actually distinguish them apart is due to, it turns out to be this equation right here. It's called Rayleigh's criterion. And basically, it occurs when the first dark fringe of one object's single slit interference is over top of the central bright of the other one. So in other words, if you have that single hole, you have the 2 objects. Is there a good picture of this? Well, yeah, there you can see them messed up with each other. But the idea is you have a single slit that they're coming through. In this case, it'd be a circular aperture. And so you have like one object here and one object like here. And so the light from one comes through and spreads out and makes its, you know, single slit interference pattern. And the light from the other one comes over here and spreads out and makes its single slit interference pattern. And you can just tell them apart if this, let me see, if this bright fringe here is right over top of that first one's dark fringe, that you can tell them apart. Because otherwise what happens is you end up with, this is one of them's single slit interference, And then the other one, single slit interference, is just slightly off like this, right? And then that wasn't very good. It's just slightly off. And then what happens is you end up seeing a superposition of those, and all you see is just slightly bigger, and you can't tell. It looks like, you know what I mean? When those overlap with each other and combine, they look like one object, right? And so you have to actually get them spread out enough such that if you have like one right here, right, then the other one has to have its bright like that, where this is lined up with that and that's lined up with that. And then what happens is you get some sort of resultant that, you know, kind of looks like this kind of a thing. And you can tell that there are now two things because you have the two separated peaks. They're separated enough for you to be able to tell. It's a little bit arbitrary, I guess, but it is, you know, you pick it where that one meets the other one, and then it actually does become pretty distinguishable. Okay. Note here, the size of the spot increases with wavelength and decreases with the size of the aperture, and you'll see that as we get to the equation for this. And there you can see it. On the right, you can tell it's two different sources. On the left, you could not. They're not resolved on the left. They could just be one light source, or not fully resolved, I should say. Okay. So here you're still not sure here on the left if it's a motorcycle or another car. But as it gets closer, you're like, oh, it's a car. All right. Next is diffraction gratings. So think of a double slit turned into a triple slit, turned into a quadruple slit, and so on and so forth. You just keep adding a bunches of slits. And as you do this, what happens is your peaks really all start to cancel out, because what you do is you end up with, you know, one single slit like this, and then you have the next single slit like right next to it, and then you have the next single slit right next to it, and they start canceling each other out in between. And so then what you end up with is you end up with a very bright spot, and then all in between for a while they cancel each other out, and then you get another bright spot, and then they cancel each other out a bunch. Oops. And then they cancel each other, and then you get a bright spot. And then they cancel each other, and then you get a bright spot. And that's what they're showing down here, is you get this system of bright spots. And what's really interesting, if I can show you this in the lab next time, is this is, a lot of people, you think that this is a shadow, but it's not a shadow, it's an interference pattern. And when we get in the lab, I'll show you exactly what I mean by that, by saying that. Yeah. You mean the rays of light coming through a cloud? Yeah. No. That's more like just diffraction through. Those haven't like spread out enough to then diffract and interfere with itself. So. No, that's just light coming through slits. That's not the interference pattern there with that. This is more like if you want to do this for like breaking up different, like say you're looking at hydrogen, and you want to look for where it's peaking, and you split the light apart with a diffraction grating. And because for different colors, these light peaks will be at different places, and it'll break it up into a rainbow. So you ever had those glasses you put on, and then you look at a light and it looks all rainbowy? That's this. Or y'all ever done like diffraction to identify an element, and you look for the where it has because different elements can absorb and emit different lights based on their orbital differences, right? So if it can jump an orbital, it can either emit that light or absorb that light. And so if you excite it, it will emit those light. And so you can look at the specific light, break it apart into its rainbow like that, and look at the specific wavelengths that are appearing, and then correlate those back to specific wavelengths of those same energies for those same light levels. And so different elements and different molecules and stuff will have different wavelength patterns because they have those different orbitals. And so they have different orbital transitions. And so they have like it's like a very clear fingerprint of what that is, of what element that is. Y'all have never done that? You've never done a diffraction in chemistry? I feel like that you would do that to identify elements. Okay, whatever. So anyway, you end up with this. You have your 0, 1, and then you can go left or right to the other bright spots. And again, if something like blue was on here, then blue would have, I can't remember which way it would be, but blue would have its peaks at different locations, at different angles and stuff like that. And so you could split this up into a rainbow and then tell what corresponding light ones were, because they have different different indices of refraction. Okay, and so here it is. You can see it's coming out of a bunch of different slits here. And then that's your equation right there. It's the condition for constructive interference in a diffraction grating, d sine theta, and then m lambda. So you'll have your first one right in the middle, and then you can go up or down by the same angles in either direction. Okay? And so that's essentially what you'll get if you shine a single color of light through it. You'll see like bright spot here, bright spot here, bright spot here, bright spot here. And if this is your central one lined up with the center of your light source, then you get these other angles, theta, and so on and so forth, that it's going to go over to. Okay? Theta, 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 theta. Well, like that. Okay? Different ways. There's a lot of different ways you can make these diffraction gratings. Some are carved, some are, some you can do an interference pattern already onto something and make a bunch of lines onto it, like some sort of photosensitive paper, and do an interference pattern onto it and make your own diffraction gratings that way. Some are carved like it's a piece of glass and then it's shaped like this. Some are shaped like this, and then they talk about like blaze angles and stuff that go along with it. But anyway, you can have all different kinds of different ones that you can make. Here they're talking about using acoustic wavefronts as that. The other thing you can do with this is use it in another way to identify elements, because if you have something that has a crystal lattice, it will actually, and I feel like this is one of the worst things I ever had to try to understand. I think the worst class I ever took in all of my life in graduate school was solid state, and it was horrible, because if it actually made sense to me, right, I think this is the class that I just had the most trouble with. Is essentially the idea is you have a bunch of particles inside your crystal lattice, and if you go to reciprocal space, points become planes. And therefore, in reciprocal space, those points become planes. Those planes act like a diffraction grating. You can send a light into these reciprocal lattice planes that then will interfere with themselves and create an interference pattern when you hit them with X-rays as they bounce inside these planes. You can then look at that and see a very specific set of peaks for the element or whatever it is you're looking at, in case it's something like iron oxide that you're not going to be able to get light coming off of. So you send this X-ray into it, and then you get that, and then you can figure out, what kind of a crystal shape it is and all that kind of stuff based off of that in the reciprocal space, and then you take that and move it back into the original space, and then you get the locations of all the atoms in the crystal lattice. It was horrible. Horrible. It was the last test I ever had to take. I didn't start recording again. The angle, no, this is assuming it's coming in straight on. I know we draw it a little off, because otherwise what you'd be doing is saying, all right, here's my angle, and then you'd be saying, all right, here's my incoming, here's my outgoing, here's my transmitted, here's my reflected off the transmit. You know what I mean? So we draw it more like this, like that. But it's really, this is done such that the light is coming in straight through. If it's coming at an angle, if it was actually doing an angle like that, we're assuming a shallow angle. If it was coming in at a big angle, then of course it'd be different, because, if it came in like this, then the film thickness is much, much different than this, right? Like this thickness from here to here is not that different than here to here. So if we're close to being perpendicular to it, then this is pretty good. If we're at a very big angle, it's going to make a big difference. And it's probably not going to bounce back on itself, but then the next ray that comes in, it'll interfere with if it's the same color. You know what I mean? Because this isn't a single point of light. It's a, you know, it has a thickness to it. Okay. Anything else on this one? All right. For the next one, we have camera lenses and sometimes even people's glasses. You ever see people's glasses and you look at them and you can see like a reflection, but the reflections are only a few different colors? They do this. They put different coatings on it. You put different coatings of different thicknesses to then cancel out the reflections. You see less reflection. So instead of like all the light reflecting, only a few colors in. And the more coatings you put, the more different colors you can reflect out or you can cancel out. So camera lenses N equals 1.52 are often coated with a thin film of magnesium fluoride, which has an index of refraction of 1.38. The non-reflective coatings use destructive interference to reduce unwanted reflections. Find the condition for destructive interference in this case, and calculate the minimum thickness required to give destructive interference for light in the middle of the visible spectrum, which would be the yellow-green light of 565 nanometers. So if we look at this above, we're going to have a phase change occurring twice, because the first one is high speed to low speed, so we get a phase change. So this one is a phase change, and then this one again is middle speed to even slower, so we get another phase change. So both reflections phase change, which means the two phase changes cancel each other out. So that means that for destructive interference, we want to go ahead and use the one that has the 1/2 in it that looks like destructive interference, right? Because we have the double phase changes. It's like a double negative, right? They cancel each other out. Again, I only keep getting like 1 or 2 head nods. Does that make sense or no? No?
Why do they cancel each other out?
Because both of them. So remember that one picture I was drawing where I said, oh, okay, I have this wave here and I have this wave here. And I took this first wave and I flipped it over. I phase changed it. But now this one also gets flipped over. They're both getting phase changed, which means all we care about is the path length difference. And therefore we want them just straight up destructive interference. So we want that -1/2. If we only have the one phase change, we're essentially using the constructive interference equation for destructive interference, which is why back here, we didn't have the -1/2. But over here, we have 2 phase changes, so we're going ahead and using the destructive one as destructive. We're using that -1/2 version. Now, is that clear? Okay. All right. So we'll use this one for destructive interference. We come down here, and I was putting over here that like N1 is less than N2, which is less than N3, which means V1 is greater than V2, which is greater than V3, right? Low index means high speed. Now, we come down here, they tell us the wavelength in vacuum, 565 nanometers. They give us the index of refraction of the material that it's inside. So it's not the index of refraction of the air, it's not the index of refraction of lens, it's the index of refraction of the magnesium, because that's the one where we're paying attention to how many wavelengths it travels. Okay, so that's the wavelength we want. We want the magnesium one, not the air or the lens. Does that make sense? Because that's the one we're looking at it traveling inside of, where we're interested in its changed wavelengths and how many path lengths it goes through in that film. Right? Because we're not, because after it passes into the lens, we don't care. It goes on off through to your eye and it's not a big deal anymore. And during in air, we don't care about its path length difference there. We only care about it inside that thin film. So that's the index of refraction we're using there. We're looking for minimum thickness, so we'll use M equals 0 for this destructive interference. And then I just plugged it in. 2nt over lambda v minus 1/2 equals M, which is 0. And then solve for t. T equals, add the 1/2 to both sides, multiply the lambda v over, divide the 2n over, plug your numbers in. 102.4 times 10 to the -9th meters. which is 102.4 nanometers. Any questions on this one? Anything unclear?
Just like random, does this have to do with like polarized sunglasses?
No. Sorry.
That.
Huh?
What is that?
Polarized light is that's like an hour-long discussion there.
Okay. We have 5 minutes.
Yeah.
So just not this.
Not that.
Okay.
Not this. No, that's more like cutting. Light is either like it can be polarized up like this, or the waves going like this, you could think of it, or the waves going like that. And so that's more like, say I had a set of blinds that were horizontal. If I wanted to get this pin thrown through it, right, would I want to throw it this way or this way? If I throw it this way, it's not going to make it through. If I throw it this way, it'll make it through. So that's more what polarization is. So the sunglasses that are polarized, what happens is when light reflects off a surface, it reflects off parallel to it. So when it reflects off like the water, it reflects off polarized this way. So if you have a vertically polarized lens over your eye, it can't get through and it blocks that out. But the rest of the light coming around is polarized in every other angle, and so a lot of it can make it through. And it's the same thing for 3D movies. They'll polarize one eye this way and one eye this way. And so when you're watching the movie, they switch frames, they switch the polarization. So one eye gets one frame, the other eye gets the other frame because of the different polarizations. And if you're in one of those, and you turn your head like this, it gets blurry because suddenly all the light's coming through both of them. Except then they started doing, to prevent that, they started doing circular polarizations. One's left polarized and one's right polarized. So you can turn your head like that and it doesn't mess up the screen.
Okay. And that's also why you have to have like good eyesight in both to like look at a 3D movie, right? Because like it does rub off the pole.
Why you have to have good eyesight?
Like in both eyes. Like if one eye was like worse,
Then like, yeah, one of your depths would be messed up. Yeah.
okay.
Don't go with just one contact lens in.
Yeah.
That would probably not be good. So, all right. Any other questions on this one? Okay. Let's see if we can get through this one here. Light with a wavelength of 511 nanometers forms a diffraction pattern after passing through a single slit with a width of 2.2 times 10 to the negative 6 meters. Find the angle associated A, the first, and B, the second dark fringe. So this is our equation for a single slit right up here. And then M equals 1, 2, 3, 4, plus or minus 1, 2, 3, 4. So M equals 1 is going to be the first dark fringe there. And so we come down here, W, they tell us, is the width of it, 2.2 times 10 to the negative 6. And they tell us the wavelength is 511 nanometers. What is theta? For the first dark fringe, it's just a matter of plugging that in with M equals 1. That's right here. Plug it in with M equals 1, and you get 13.43 degrees. Then you come down here, and for the second dark fringe, you do the same exact thing, but with M equal 2 lambda instead of just lambda, and undo. And you'll get 27.68 degrees. Okay? Not exactly doubling because we're taking that arc sine of it. Any questions on that one? So maybe conceptually difficult, but mathematically pretty simple. You just have to remember which order numbers, which go with what, and which equation. So these tend to be easier than the ones we were just doing with the interference through thin films. I don't know. These tend to be a little more straightforward, I guess, in solving. You don't have to think about, well, how many phase changes did I have and stuff like that. Okay, you're just pretty much straight up using that equation. Next here, here you have a single slit experiment. Light passes through the slit and forms a diffraction pattern on a screen 2.31 meters away. If the wavelength of the light is 632 nanometers and the width of the slit is 4.2 times 10 to the negative 5th meters, find the linear distance on the screen from the center of the diffraction pattern to the first dark fringe. So in the last one, we were just finding the angle. Now what we have to do is take that angle and find how far off to the side it is once it reaches that screen. So if you look at my picture here, you can see this is the angle we would be finding right there. But now what we're going to do is use this distance to the screen to figure out then how far over on the screen we have to go to get to that one. So it's essentially doing the exact same thing as I did on the previous one. Use the same equation, W, all these kind of things. And the first thing I did was find theta, just like I did on the previous one, just with different numbers. After that, I said the tangent of this angle is equal to L divided by D, which means L equals D times the tangent of theta. We just found theta, so then I just have to go through and plug in. So it's essentially doing the exact same problem, but then going in and doing a little trig, doing a little geometry or whatever, right triangle, I have the angle, I have the length of one of the sides, what's the opposite side? And I just use tangent to find it. So 0.0348 meters. So about 3.5, 3.5 centimeters. You'd have a bright spot, and then 3.5 centimeters away, you'd have another bright spot. Okay? So Friday, we'll pick up from there. Take a look at the rest of these and even from the last chapter. And we'll just review whatever questions you want to do on Friday. Friday's our last day before the test, right? Okay, so review day on Zoom. You can email me questions ahead of time if you want to get them to me so that I know to go over them for you, and I'll make sure we get it, okay? Otherwise, bring them with you and we'll go through it. Have a good one. What's up?
So last week, sent you an email